Alright, this is done the last couple weeks of working FRQs here, so keep after it. This is 2013, is number 3. They give us an equation. The student is looking for enthalpy changes, so we're dealing with delta H's. Magnesium oxide reacts with HCl from the net ionic equation above. They do coffee cup calorimetry, just like we did in class. And so they have volume of HCl here, they're adding magnesium oxide here, initial and final temperatures, and they ask us in A, which one is the limiting reactant in all 4 trials, HCl or magnesium oxide, and justify your answer. And so you can do this a couple different ways. The first way, just through explanation, you can say changing the mass of magnesium oxide is causing different changes in temperature. The changes in temperature are based on the limiting reactant, so the fact that these guys changing causes different changes in temperature must mean that's a limiting reactant. I calculated it, and so all I did, and this calculation will help a little later, all I did is take and turn it into moles of HCl and moles of magnesium oxide like this. We have 1 molar HCl. In every trial we have 0.1 liters of it. So we have 0.1 moles of HCl at the beginning of every one of these experiments. The most magnesium oxide we use is 0.5 grams. So if we use 0.5 grams of magnesium oxide and go grams to moles, we have 1 mole for every 40 grams of the magnesium oxide, and so that equals 0.0125 moles of magnesium oxide. So the most magnesium oxide that we used in all the trials was this much, 0.0125. And so that 0.0125, there is a 1 to 2 ratio, is equivalent to us needing how much HCl to react with that? 0.025 moles of HCl needed. It's a net ionic equation, right? So you don't see the chloride, but we need this much. So we have way more than we need. And so doing that work and showing this is how much HCl, that's how much HCl is needed, then you need to write down magnesium oxide must be the limiting reactant. For us on this test, because we're not going to do a lot of math, I could see them asking that question and not having you do calculations. And so the limiting reactant determines the change in temperature. Because there's a fluctuation in different changes in temperature, that means that this guy must be the limiting reactant. If this was the limiting reactant, the change in temperature would be the same every time. So that's part A. Part B says one of these sets of data is inconsistent with the other 3 trials. Identify the trial that's inconsistent and draw the line through the data from the trial. Because I know this is the limiting reactant, these 2 should make the trial 1 and 3 should both make the temperature change the same. This one increases by 1 degree. You can even do a delta deal. That's 1 degree Celsius change. This guy is 2 degrees Celsius change, and so I know one of those has a problem because those should be the same. Because we doubled the amount of magnesium oxide here, this should double the change in temperature. These guys both happen to be 4 degrees. That's double of this one, which means trial 1 there is my inconsistent one. It asks you to cross out the inconsistent one. We would just draw a line through it on the test. And then it says explain how you identified the inconsistent data. So I put trial 1 is inconsistent because temperature change should be proportional to the magnesium oxide added. Trial 1 should have a temperature change of 2 degrees Celsius. It's about understanding that the temperature change should be proportional to the magnesium oxide added. That's part B. Then part C says, for part C and D, use the data from one of the other 3 trials. You can use it from any one. I would identify which trial I'm using it for. And it says, assume a calorimeter has negligible heat capacity, gives us specific heat. The density of HCl is 1, so that we can turn that volume from milliliters to grams, and we can use that to calculate the Q. And so here we go, we are off and running. That's the specific heat contents of the calorimeter is this. Perfect. HCl is 1. So on part C, it's Q equals MCAT. We have the mass here. And so our 100 milliliters of HCl we turn into grams, right? And I don't even know that you have to show this work, but 100 mils, and it tells us this is milliliters to grams is 1 gram per 1 milliliter. So if you don't show that work, that's okay, I think. The mass of that solution is 100 grams. They didn't include the grams of magnesium in there. Specific contents of the calorimeter, and so whether you include that half a gram or not doesn't really matter. I'm going to do this for trial 2 just because it's the next trial on the page. So 100 grams, and then we got the specific heat constant. That's the 4.18 joules over grams degrees Celsius. All times our change in temperature. Our change in temperature in trial 2 was 4.1 degrees Celsius. And so our Q for trial number 2, I'm going to plug it into my calculator, is 1.71 kilojoules of energy. That's my Q value. If you did trial 3, trial 4 should be really close to this. Trial 3 is about half of that. It's 0.88 kilojoules if you did trial 3. So there's trial 2. That's what I did. That's part C. Part D says determine the student's experimental value delta H for the reaction between magnesium oxide and units of kilojoules per mole of reaction. This is why it was so nice that we calculated the moles of the magnesium oxide here, because all we have to do then on part D is take our kilojoules, our 1.71 kilojoules, that's how much we got for half of a gram, and now we want to do it for per mole. So we're going to divide that 1.71 divided by, how many moles did we come up with? 0.0125 moles of magnesium oxide. That's for one mole of magnesium oxide, and that will tell us that we have negative 137 kilojoules of energy per mole of reaction. You have to be careful when you do delta H's, and that's what they're asking for. Sign matters here. Okay, so make sure you have your sign on that problem. With Q's, it doesn't matter because it's a change in heat energy one way or other. But delta H's, you need to tell whether they're endo or exothermic. So this guy equals negative 137 kilojoules per molar reaction. And the beauty is, if you did trial 3 this way, it also equals negative 137 kilojoules per mole because you used half as many moles here. And so the answer shakes out the same either way. Part E gives us a chart with enthalpies of formation for each of these pieces of the reaction. And it says, using that table, determine the delta H for the reaction of magnesium oxide. So we got to plug this back into the equation that we have up top for E, and we are going to do delta H. So I'm going to write it for us. Delta H of this reaction is going to equal delta H of products minus the delta H of reactants. Products minus reactants, unless it's bond energies. And so our delta H for reaction, I'm peeking at the equation here. Our products are the magnesium ions plus a water minus the delta H's here of magnesium oxide and 2 of those hydrogen ions. And just be careful of signs here. Now the nice part is the hydrogen ions there are 2 of them in the equation, so be careful. But hydrogen ions, they're considered a pure element here, and so they have a delta H of 0. And so we just have to plug our other values in. And so our delta H of our reaction is going to be the magnesium ions, -467. These are all in kilojoules per mole, plus the water, -286. All minus that magnesium oxide, careful with your signs, minus the 602. And we plug that all in, and I encourage you to plug it in. Don't take my word for it. Plug that guy in, and you get -151 kilojoules per mole for that reaction. That's part E. And if you're decent at anticipating questions, then you just figure out experimentally it's -137, and theoretically it should be -151. And so now they're going to ask us, all right, where's the difference? Why is there a difference? And that's where part F is taking us. And part F says the accepted value and the experimental value do not agree. If the calorimeter leaked heat energy to the environment, would it help account for the discrepancy between values and explain? The answer is yes. If it leaks heat, it would. And the reason is because the change in temperature would be recorded as smaller than it is. Would be smaller. So our Q value would be smaller, and delta H, the experimental one, would be less than the accepted value. It's fighting back through the numbers, right? If we come up here, if we lost heat somewhere else, then not all that heat was absorbed by the water. And so that number would be smaller. That makes this Q number smaller. That makes our delta H of our experimental value smaller. And that's what they're saying happened in this case. We must have lost some heat. So let's look at the question again, make sure we answered it. The accepted value don't agree. If the calorimeter leaked heat energy, would it help account for the discrepancy between values? Answer the question, yes it would, because the delta T would be smaller. So our Q value would be smaller, and the experimental would be less than the accepted value. That's it. That's 2013, number 3. Hang in there. Keep fighting.